So here's what we're going to talk about. I'm going to start with a description of the data set because it's a simulated data set that goes with a little story. Yeah, I can tell my mouth's drying out already. And then we're going to either review or introduce some new concepts. Unobserved confounding and endogeneity. Anybody familiar with this? Actually, how many of you have used Stata before? Oh, good. How many of you have had any econometrics? Some. How many of you have heard of endogeneity before? Oh, well, we don't need to do this then. That was a new topic for me. So anyway, we're gonna start back our review of unobserved confounding and endogeneity. Then we're going to talk about non-random treatment assignment and then data that are missing not at random, which can lead to something called selection bias. And then we'll wrap up and talk about treatment effects. So the data, this is completely fake data. So don't believe anything you're about to see. But this is the story that goes with the data set. Fictional State University has developed a new study skills program with the goal of improving the students' grade point averages. Okay. So the treatment is the study skills program, the outcome of interest of students' GPA. So that's, oh, thank you very much. Okay, water. And so these are the variables in this data set, and you can download all of this stuff. It's in that download, the data set's in there. So the first variable is ID, and as you might expect, it's just an identification number for the students. GPA is the student's final college GPA that we collect when they graduate. HSGPA is high school grade point average that we collected when they applied to school. Program is an indicator for program participation, so whether or not they participated in our study skills program. Graduate is an indicator for whether or not they graduated. Some of the students didn't graduate, as we'll see shortly. Income is a measure of the parents' income is a measure of parents' income in hundreds of thousands of dollars to keep the numbers small. Computers don't like big numbers, so we're going to shrink it. HS Comp is a measure of high school competitiveness. Now, when I created these slides back in 2019, I made this up. It's a completely fake made-up variable. But I've done this a bunch of times now, and someone's told me that the College Board has developed an official measure of high school competitiveness. I wasn't aware of that when I made this. That's not what this is, so it's just a made-up variable, and it's continuous. Roommate is an indicator variable for whether or not the student's roommate is also a student. And then scholarship is an indicator for whether or not the student received a needs-based scholarship. Can you guys read this in the back of the room? Is it too small? Oh, okay. Because I'm just kind of looking at it going, it seems kind of small. I don't know if you can read it back there. Okay. So the first thing I like to do with a new data set is just summarize it. And the main thing I'm looking for here is the OBS column. I want to see if I have any missing data, because often that's the first fork in the road when I do some sort of data analysis. Do I have complete data, or am I going to have to deal with multiple imputation or FIML or something like that? And as I scan down the OBS column, the first thing I notice is I have complete data, 1,000 observations on all the variables except for GPA, college GPA, which is unfortunate because that's my primary endpoint. That's the thing that I'm really interested in. But I have complete data on everything else. So we're going to come back and deal with that later. But 792 observations for GPA. So I'm going to go through and just kind of get to know my data first. I like to look at descriptive graphs and tables. So I'm going to tabulate graduate. And the first thing that jumps out at me is that 792 students graduated. 208 did not graduate. Well, wait, 792, that's the same number that I have for GPA. So there must be a relationship there. And we'll come back to that later on, but that's more than a coincidence that 792 graduated, and that's how many observations I have for GPA. This is your first clue that these are fake data, because this is a histogram of college GPA, and it looks remarkably normal. There are no outliers. There's nothing weird about this, but I like to do, and it doesn't have to be normal, but I just like to check data to make sure I don't have multi-modes or any kind of wild outliers or anything like that. But if you see data like this in real life, you need to scratch your head and say, what's going on here? Another thing I like to do with new data sets is create a scatter plot matrix of any of the continuous variables that I'm going to be using in my analyses, because often this will show patterns that are nonlinear and things like that. And so this is uh, college GPA, high school GPA, the laser doesn't work, college GPA, high school GPA, and parents' income. The first thing that jumps out at me here is that there seems to be a strong association between high school GPA and college GPA. No surprise there. If you did well in high school, you probably do well in college. But it's a feature of the data. We're just getting to know our data set for now. Parents' income looks like it's pretty strongly related to high school, at least somewhat anyway, and a little bit related to parents' income is somewhat related to college GPA. So again, just getting to know our data and the patterns there. Now, I know a lot of people hate pie charts, and I'm not a huge fan, but for two categories, I think this kind of presents it nicely. This is the number of people, or the percentage of people participating in the study skills program. Well, what strikes me here is only 30% of the people in my sample participated in the study skills program. And if I didn't look at this, I might make the assumption that it's 50-50, because if I was doing an experiment, I would probably randomly allocate 50-50, but this is 30-70. Only 30% of my sample actually took the study skills program, the intervention of interest. So again, just a feature of the data. So box plots, I like box plots for exploring data as well. So here the horizontal axis is final college GPA, that's our endpoint of interest. And here I've done this by program participation. So did they or did they not participate in our study skills program? Well, this is a little troubling because according to this box plot here, the students who took our study skills program had lower median GPAs than the students who did not take our study skills program. And that's disturbing because the whole point of the study skills program was to help improve college GPA. And this suggests that it lowered it. Is it causal? Is it correlational? I don't know. But nonetheless, students took our program and they tended to have lower test scores or lower college GPA. So that's kind of disturbing. And in fact, if I fit just a simple linear regression model for this with GPA as the dependent variable and program as an indicator, I get a negative coefficient on program participation. So that suggests that, like, I've already said it twice, but something's weird here because our intervention shouldn't harm their GPA. But let's look at high school GPA by program participation. So high school GPA was collected before the students took our program, our study skills program. And here, people who took the study skills program had lower incoming high school GPAs as well. So if you think about the temporal order, high school GPA is measured, then they take the study skills program, and then we get their college GPA. But here, the study skills program could not have lowered their high school GPA because temporally it doesn't make sense. So something's going on here. So just for fun, let's fit a regression model again for GPA and program participation and put high school GPA in the model. And sure enough, when we do that, the coefficient for our program participation flips to the positive side. So there's some strange relationship going on there. But again, we're just getting to know our data and kind of fitting some basic models. More patterns in the data. The horizontal axis here is the percent of students graduating. The students who participated, of the students who participated in our program, 69% graduated. Those who didn't, 83% graduated. This doesn't look good for our program. Things are not looking good so far. This is high school GPA on the horizontal axis and graduation status. So of the students who graduated, they tended to have a higher incoming high school grade point average. So again, just features of our data. I like to get to know my data before I start building sophisticated. But the question that we really want to answer here is, what was the effect of the study program on final college GPA? So clearly we have some strange issues and patterns in our data that we need to keep in mind as we go through and start fitting these models. So the first thing I want to talk about is unobserved confounding and endogeneity, which it sounds like I don't need to because you guys already know this stuff, but let's kind of review it anyway. So let's zoom way out and talk about regression sort of from first principles. Let's say and forget about GPA for a moment. Let's just talk about some arbitrary variable y. Y, when we fit a regression model, we're saying that Y is equal to all of the possible factors that could influence Y. We're going to separate those into two groups: the observed factors, the things we have in our data set, and the unobserved factors, things we didn't observe or they aren't in our data set. And the observed factors are usually the variables, the X's and things that we actually put in our model. But all those unobserved factors get sort of thrown into the statistical garbage can that is our error terms or our residuals. And I don't know about you, maybe I was just trained poorly, but as a biostatistician, we never really gave a lot of thought to what was in the error terms. It was just how far off are my observations from my model, and that was kind of the extent of the thought we gave it. We never really thought a lot about the unobserved factors, okay? But we're going to come back to that and think about the unobserved factors in a moment. So first, let's define endogeneity. Jeff Wooldridge, in his Intro Econometrics book, defines endogeneity as an explanatory variable in a multiple regression model that's correlated with the error term. That's just a simple definition of it. So if I have a covariate Z in my model and it's correlated with the error term, I would say I have this issue of endogeneity. So that's the definition, but how does this happen? Well, there are a lot of ways it could happen. One of them is called omitted variable bias, and this is how omitted variable bias works. So let's say I have two covariates in my model, X and Z. X and Z could be correlated, and this happens all the time, right? It's just multicollinearity, very common phenomenon in regression models. But let's say that for whatever reason, Z doesn't make it into our model. Maybe we didn't collect it, or maybe we just decided not to put it in, but for whatever reason, Z doesn't make it into our model. Z doesn't disappear into thin air. Z moves from being in the observed part of the model into the unobserved part of the model. It's still in the model, it just moved from the observed part to the unobserved part into the error term. So in the model in the middle here, now I no longer have Z and the observed part. Z gets bundled up in error star. Well, if Z is correlated with X and Z is now part of error star, by definition, the error term and X have to be correlated because Z is now part of that error term. So that's one way that you can end up with endogeneity. There are others, and we'll save those for another day. Now, why do we care about this phenomenon? Well, as the name suggests, omitted variable bias, if we have this problem, it can actually bias the other parameter estimates in the model, beta 0 and beta 1. We would estimate them with some possible bias. Maybe, not for sure, but maybe. So this is something that we want to be aware of. Now, if you come from another field, such as epidemiology, you may use different terminology. So let's come at this from another angle, namely confounding. Now, when I went to make this slide, I thought I was going to make this slide and move on. I thought it would be just quick because I knew what confounding was. It turns out I did a deep dive and spent about a day trying to put a definition on this slide. Sander Greenland and the Encyclopedia of Epidemiology claims that there are at least 3 different ways that epidemiologists use the term confounding. And one of the references, I think, in that thing in the entry in the encyclopedia led to another paper on the history of the use of the term confounding in the world of epidemiology, which is an interesting read. My point is, this is not a well-defined term, it turns out. So I'm going to use, this is the term or the definition we're going to use from today, and it comes from Judea Pearl's book on causality. So according to Pearl, X and Y are confounded when there's a third variable Z that influences both X and Y. So if I have Z in my model, of course I think Z influences Y, or I wouldn't have put it in my model, but Z may also influence X, and if that's so, then I have confounding. Okay, so that's our definition of confounding we're going to roll with today. Well, what happens if Z is not in the model? Well, it's a similar phenomenon. If Z is not in the model, it moves to the unobserved part of the error terms. And if that's the case, we have a phenomenon called unobserved confounding, which is basically the same thing as endogeneity. And it's just omitted variable bias, whatever you want to call it, but this phenomenon could lead to biased estimates of beta 0 and beta 1 and other things in our model. So it's a phenomenon we need to be aware of, and we also probably want to figure out how to deal with this. So what does this have to do with our GPA example? Well, let's say start back with GPA from first principles. Let's say that GPA is equal to all of the possible factors that could influence someone's college GPA. And we're going to split it into observed and unobserved factors. So the observed factors could be things like someone's high school GPA, SAT scores, parents' income, sex, the things we have in our data set. But let's actually stop and think about the unobserved factors. What are those things that are lurking in our error terms? They could be things like ability or motivation. I need to take sleep out of here because smartwatches nowadays can monitor your sleep. But emotional support. How do you measure emotional support, or how do you measure ability? We talk about these things, and we sort of believe they exist, but defining them and measuring them is a little more abstract. Think latent variables, which we're going to call it here in a moment. So if we have these other unobserved factors, and we're going to think about those, what do we do with them? Well, let's think about ability for a moment. Let's just stipulate that ability is something we believe exists, and we believe ability influences your high school GPA, and we also believe ability probably influences your college GPA. And if if that's the case, then that means ability here could be an unobserved confounder, if that's the case. So what are we going to do with this, and how are we going to know if this is a problem? Okay, this slide is a little scary because there are a lot of funny symbols and a bunch of math-looking things on here. But here's what we're going to do. We're going to take this model at the top. So I'm going to say GPA is equal to parents' income, high school GPA, plus this error term that contains ability bundled up in it. I'm going to take high school GPA out of the original model and split it off into an auxiliary model. Okay, so now I have a model here where high school GPA is the dependent variable, and I'm going to put a special variable in that regression model, in this auxiliary model. And I need a special variable that has a couple of properties. One, I need that variable to be associated with the outcome, high school GPA, but I need it to not be associated with the unobserved confounder ability. So I'm going to put high school competitiveness in here, and this is the argument I'm going to make why it fits the role here. High school competitiveness could influence your high school GPA. Maybe the more competitive it is, the lower your GPA, or higher, I don't know. But high school GPA seems like it could influence your high school competitiveness, could influence your high school GPA, but it's not likely that it has anything to do with your ability, because high school competitiveness is a feature of your school, not of an individual. So that's the argument I'm going to make here. High school competitiveness fits the bill for this variable that we need. Then what I'm going to, question?
Just to play devil's advocate, because you could argue parents definitely move to schools based on the high school competitiveness.
Yes. Let's not think about it too much. Let's not deal with reality. This is our own little fantasy world.
So
you're exactly
parents
right.
can observe their kids' ability, right?
You're exactly right. That's why I emphasize this is a made-up example, but you're absolutely right. Okay, here's what I'm going to do, and this is kind of a mathematical leap if you're not familiar with this. This green part of the model here is the expected value of high school competitiveness, right? So this is what I observe, this is what I expect, and that's the residual part left over. What I'm going to do is take this expected value, the expected high school GPA, I'm going to substitute that into my original model. So rather than putting high school GPA in my original model, I'm going to put the expected value of high school GPA in the model, okay? By doing that, I remove ability from high school GPA. I've split this into two parts, and now I don't have this issue of having ability bundled up in here, so that removes that correlation. So that's the idea. That's what we're going to do. So now we have two models. We have our original model and our auxiliary model, and the expectation of this goes in here. So if that's the case, these two models both have their own error terms. So the top model, the auxiliary model, has an error term that contains ability, and we're going to call it epsilon 2. So the whole thing is the error term. The main model also has an error term that contains ability. If they both contain ability in the error term, then that means that they should be correlated. So let's think about this in a different way. Let's take that model. How many of you are familiar with structural equation models at all? I could just go take a break. You guys could teach this stuff. Okay, so I really don't have to explain path diagrams, it sounds like. But I didn't see everyone's hand go up, so just really quickly, a quick review. Things that have corners on them are observed variables in our model. Things that are oval or round are the unobserved part. So I have the error term, okay, drawn as a circle, and I have this oval thing called a latent variable. That's the thing that we wish we had measured, but we didn't. We're going to call ability now a latent variable. The arrows between these are similar to regression coefficients. They're path coefficients, and you can interpret them the same way. So I've drawn the top model as a path diagram, and here's what I want to do with it. Now I want to split the model out into two parts again. I have my auxiliary model, and I have my main model. And if I draw them all this way, as a path diagram, now I can see that I have these two error terms, and I've drawn ability again as a latent variable. And I believe that ability is influencing both high school GPA and college GPA. So how am I gonna, I could fit this model like this, but another way to think about this is just to think of the correlation between the error terms. So if you don't like the latent variable approach to it, maybe think of the errors this way. These are the two errors from the auxiliary model and the main model. Both of those contain ability, and so if they both contain ability, there's an overlap in those errors. So the overlap there is correlation. Okay, these error terms are going to be correlated. So what I can do then is I can fit a model where I allow the error terms to be correlated, and if they are correlated, that suggests that I have this problem with endogeneity. Because if I don't have this unobserved confounder lurking in the error term, then they shouldn't be correlated, right? But if there is this unobserved confounder lurking in the error terms, then these two are going to covary or be correlated, and I can estimate that correlation and see. So we've gone this far down this road. Let's just keep going with the structural equation modeling approach here for a moment. So I've drawn the structural equation model and stated sim builder. I'm going to fit the model, and lo and behold, the correlation between these error terms is 0.88. That's pretty high. So that suggests that I have this problem with endogeneity. There's some unobserved confounder lurking in both of these error terms that's making them correlated. So now we've identified, now we've identified the issue. What do we do to deal with the issue? How do we solve this? Well, the good news is the model that identifies this problem is also the solution to this problem. If we fit the model this way, the parameter estimates in the rest of the model actually become unbiased or consistent or whatever you want to call it. At least they should be, assuming we don't have other unobserved confounders lurking in the model. So, so this is a way that we could both identify and solve this problem, okay? Now, there's another approach to this, and I should have mentioned that this command I'm going to show you was written by econometricians for econometricians, and it was never intended for you guys to see. And the way this talk came about actually is I was recording a video when we released this, and I started reading up on it and playing with it. I thought, wow, this is really cool. Why have econometricians been keeping this to themselves? And so that's why I put this talk together and sort of removed the econometrics jargon from it. But here's how this command works. It's sort of like structural equation models are going on in the background. And I'm going to draw these as structural equation models in the background, but you can't actually fit these using the sim command. And we can come back to that later if you want. But so there's a command that was released in, I think, Stata 15 called eregress, and it allows you to specify the primary model. And then I have this subcommand here or option called endogenous. And that's going to allow me to fit my auxiliary model, okay, that secondary model. So I'm going to put my primary outcome GPA up here in the main part of the model. I've put parents' income in here because remember when I was looking at the scatter plot matrices, parents' income is associated with GPA. But then I'm going to specify my auxiliary model down here where high school GPA is the dependent variable. And then the high school competitiveness, that's that special variable that I've put in my model. So that goes in. And then I'm going to put parents' income in there because that's also associated with high school GPA. So this is going to fit both of these at the same time. By the way, does anybody know the name of our special variable? I'm trying to avoid jargon, but it sounds like you guys know what it is. People are mumbling. Yeah, it's an instrumental variable. So I'd heard the term before, but I never knew what it meant, and now I do. So yeah, those special variables are called instrumental variables in the econometrics world. So if I run this command, the output shows me two sets of coefficients. The top set of coefficients are for the model where GPA is the dependent variable. And then the bottom, or the second little set of coefficients here where high school GPA is the dependent variable. Those are the coefficients for our auxiliary model. Then at the bottom, we get the variance of the error terms for these two models, as well as the correlation between them. So on the next slide, I'm just going to zoom in on this bottom part. So I get the variance of these error terms. There's an error term for the GPA model, the primary model. There's a variance for the error terms in the auxiliary model, where high school GPA is the dependent variable. And now I get this correlation between those two, and the correlation between those error terms is 0.75. It's different from before because I put parents' income in the model now. I didn't have that in the structural equation model. But 0.75 is still a pretty high correlation. So that suggests that we do in fact have this issue of unobserved confounding or endogeneity. But the good news is by fitting the model this way, not only have we identified the problem, but we've also fixed the problem. Because if we use this type of model, then our other parameter estimates in the model should be consistent or unbiased. That kind of makes sense. So any questions up to here? Yes.
I guess I'm confused. What did you, like, how did you know what to include in your auxiliary model? I guess that's like what's unclear to me.
Oh, so how did I come up with, back up to here, how did I come up with high school competitiveness?
Yeah.
So I know the properties of the variable, this instrumental variable. I know what I need. I need a variable that's associated with the dependent variable high school GPA, but I also need it to not be associated with ability. And so in the real world, you'd have to find a variable in your data set that sort of meets those qualifications. But when you make up your own data, you can make up your own story. And so that's why I put it in here. But in the real world, you'd have to find a variable that's in your data set that sort of meets the variable or variables. You may have multiple variables that meet these qualifications. But what you're looking for are things that are associated with the dependent variable in the auxiliary equation, but not associated with what you believe is your unobserved confounder. The econometricians in the room are kind of mumbling or thinking right now, yeah, it's not that simple. And in real life, it's not really that simple. From what I've never really done this in real life. This is the beauty of simulated data and doing what I do. I don't have to deal with reality like you do. I am told that you can encounter things called weak instruments where these things sort of meet these qualifications, whatever you want to call them. But only sort of barely, and that can lead to its own sorts of biases and things. So I'm giving you sort of just an overview and glossing over a lot of practical issues. But for now, we're just going to kind of roll with the concept so that we have an idea of how this works. Yeah.
And then in that same like auxiliary model, and a few slides later, you had income both in like the main model and in the auxiliary model. And I guess I was wondering, like, does that do anything to?
No, because they're actually separate models. Oh, let me go back to here. Yeah. So, and that actually raises another issue. So income appears in both of these models. And that's okay because they really are separate models. And if income is associated with high school GPA, I want to specify that model as correctly as possible, as well as the primary model. What I did forget to mention, though, and you just reminded me, is that high school GPA is implied to be in this main model. It only appears here, and I could type it up here. So this could say GPA income high school GPA. By putting it as a dependent variable in an auxiliary model, the expectation of that goes back into the main part of the model. So, good questions. Yeah.
So if you left income out, would the correlation between the error terms likely be higher?
It would, and the reason I know that for sure is because I did fit this without income right here. Oh, well, no, I put income in the primary model. But yeah, it's going to change it some, and I suspect it's going to typically lower the correlation if you put it in.
Right, and so it's about, and I think the practice, somebody correct me if I'm wrong, in IV models is to put the same set of controls in the main regression and the auxiliary regression. And is that really just for, essentially reducing that correlation as much as you can, fixing the things you can fix and having the model fix the rest?
The short answer is I don't know. But just using my sort of common sense or intuition, I would think I would want both models to be as correctly specified as possible, because as long as I get them correctly specified, I'm going to get better parameter estimates for both. And whatever correlation is there should also be as accurate as possible. So I guess maybe there is a rule to put everything in both models, but I would probably want to stop and think. I'd want to make them as correctly specified as possible. Think through each model separately, the auxiliary and the primary, and put in whatever need. Because there could be things that predict high school GPA that don't, like sports participation in high school. That might affect your time management and things in high school and affect your high school GPA. That doesn't really affect your college GPA. I'm thinking of my own kids. They were super busy in high school and then they ditched all that and focused on college and college. But that's just sort of my intuition. I don't have a definitive. Does anyone have a definitive answer to that question? Any other questions about endogeneity and unobserved confounding? Oh, let me back up. Okay, so I'm just showing you this because I'm collecting these models along the way. So that first model that I fit earlier, where I only put in program participation, that was the one that had the negative coefficient. I've saved the results there. Then I adjusted for high school GPA. I have those results in this table. And now I've taken into account unobserved confounding and endogeneity. We're not going to stop and look at this just yet. I'm going to collect these and we're going to take a look at the results at the end. The next up is non-random treatment assignment. So in an ideal world, what we would have done is the students would come in and we would maybe toss a coin or draw a piece of paper from a hat, and they would be randomly assigned to either participate in our study or not. So some of these students come in, flip the coin, go to the study skills program. Others you don't. The beauty of random assignment is that hopefully we're randomly distributing any observed and unobserved confounders randomly between the treated and untreated groups. And if that's the case, when we get to the end of the study and look at differences in college GPA, any difference that we observe can be attributed only to the study skills program, right? Because we've randomly distributed everything else equally. So that makes experiments really nice. It makes the interpretation of our results really easy at the end. That's not what we did. What we did is the students came in and said, hey, you want to be in our study skills program? And this person says, yeah, sure, I'll do it. Their buddy comes in behind them and they say, yeah, sure, I'll go take it too. He's gone, I'll go. Next student comes in and says, nah, I'm good. I don't have time for that. The point here is that the students are self-selecting into the treatment group or not. And that wrecks our interpretation at the end. Because any differences we see in college GPA at the end might be attributable to the study skills program, but it might be attributable to other factors that somehow got unequally distributed between the two groups. So that really screws up our interpretation. So how are we going to deal with this? Well, you might have guessed it. What we're going to do is we're actually going to model program participation. We're going to look at the factors, the observed and unobserved factors that influence someone's choice to participate in the study skills program. And we need this because ultimately we're going to put the study skills program, that indicator is going to go into our main model, right? Because that's the thing we're really interested in. And if that's the case, we need to also think through the unobserved confounding. If we're still thinking of ability as an unobserved confounder lurking in our error terms, we need to think this through as well. Does ability influence program participation? Well, maybe, because if I've been a pretty good student in high school, or I tend to feel like I'm a pretty good student of high ability, I might be less likely to participate in the study skills program. Whereas a student who struggles, and they kind of know this, someone of lower ability, might think, yeah, that sounds like a good thing for me. I'm going to go do that. So ability could very well influence someone's choice to participate in the study skills program. And we've already stipulated that we think ability influences college GPA. So if that's the case, what we're going to do then is build this auxiliary model for program participation off to the side. And just like we did last time, now this is not literal. For those of you who are following the math and know what's happening here, this is a mathematical analogy. This is not literal like the last time I did this. But the idea is the same. I'm going to take program participation, and this is going to be a probit model, because econometricians developed this, and there are mathematical reasons why we need probit instead of logit here. But I'm going to fit this model, and I'm going to, again, insert this instrumental variable. I need something that's associated with program participation, but not associated with ability. Here I'm going to use a needs-based scholarship. It's just an indicator for did the student get a needs-based scholarship? And here's my argument. If I get a needs-based scholarship, I have some extra money. So probably don't have to spend as much time, at my job as a barista. And I have more time to participate in the study skills program. I just have more time on my hands, which allows me to participate. If I don't get this scholarship, I may be too busy working and I don't have time to go take the study skills program, even if I wanted to. But a needs-based scholarship shouldn't have anything to do with ability. If it was an ability-based or that kind of scholarship, that would be different. So that's the argument I'm making here. And please don't burst my bubble. We're staying in our suspended fake reality here. So again, I have this auxiliary model set up, and again, it's a mathematical analogy. I'm going to kind of take the expected value of that and substitute it back into the original model. Not literally this time, but sort of. So this is why I really like drawing this as a structural equation model or as a path diagram, because it sort of illustrates the whole thing very clearly, at least to me. So now I have GPA in the middle. That's the main thing I'm interested in. Now I have program participation in this model, and it's binary. And I'm saying it's a predictor of college GPA, and that's the relationship I'm primarily interested in. But I think scholarship may influence program, and the reason I have to use a probit model, it's not just because they're econometricians. I need an observation level residual or error term, and logit models don't have that. And that's why we're using probit. And that's why you can't do this with stated structural equation modeling features or engines. I was told this, I didn't believe it. I wasted a day trying to prove them wrong, and I proved that it's true. You can't fit this as a structural equation model in Stata. But you can draw it as a structural equation model. So again, I'm going to allow the error terms to be correlated, because again, I'm believing that or suspecting that ability, I have some unobserved confounder lurking in both of these error terms. And if that's true, they'll be correlated. So going back to my eregress command, I still have the same primary model. And now I have two of these auxiliary models that I'm fitting. But I'm using a different option this time. I'm using the Intreat option. So Intreat allows me to fit an auxiliary model where program participation is the dependent variable. Intreat does tells Stata two things. First, it tells Stata that that's a binary variable. It's expecting either a binary or an ordinal variable, and it automatically detects it for you. The second thing it does is it identifies program as that's the treatment thing I'm interested in. And that's going to allow me to do some things in post-estimation later without having to tell it over and over again that program is the treatment variable. So the Intreat option allows me to set up this other auxiliary model, and that's going to be a probit auxiliary model. No interact, just keeps this simple. Don't worry about it for now. It's just going to keep things simple and easy to interpret. So now in my output, yes, question.
On that last one, yeah, so I just want to make sure I'm understanding the commands here. So in that one right there, if you had it identical, except before the comma that comes after income, you added HS, GPA, and program, you would still get the same results? Or not?
If you put both
Those variables
in the same
comma. No,
yeah. So both of those, that's a good question. Thank you. HS, GPA, and program both are now included, or the expectation.
I know they're implicit the way that is, but would you get an error if you actually added them and had them in different places?
No.
Okay.
Yeah, you can put them in there. And maybe I should. I don't know if it's more confusing to put them in or leave them out. I left them out because I didn't want to confuse people as to why is it there and there. It will work either way. It won't give you an error if you put them in there. Yeah. So you're doing.
Thanks.
Sure.
Question. So, I mean, the covariance, the confounder, like the primary model, you only control for income. For the auxiliary model, you only control for like income. So you argue that like you control everything, right? So, I mean, there are a lot of like other confounders may influence like HSGP.
Oh, of course. Yes.
Your argument is you control everything.
Yes, I'm keeping this super simple just so we can focus on the sort of methodology. But in real life, and the command will do this, you could put all kinds of other covariates in the model. Yeah, you would never just leave it this simple. You would put other factors in there as well. I'm just trying to pare it back to just its most basic to kind of explain the idea. Yes.
So will the auxiliary model contain all of the same like covariates as the mean model theoretically?
Maybe, maybe not. We were talking about that earlier, and I think some people may argue that you put the same covariates in both, and that may be the tradition in that world, in the econometrics world. I don't know. My point of view as a biostatistician, sort of thinking it through, is I would want to think through each model separately to make sure they're specified correctly, because if they were misspecified, then that could cause unbiased or inconsistent parameter estimates in the rest of the model. So I think it kind of depends on what department you came from. You could probably put the same covariates in both, and I doubt it would make a big difference. But I would still want to think the biostatistician. I would want to think through what are the actual things that influence those two outcomes in each model. So, okay. Any other questions? Keep an eye on the time. I don't want to run too long. But these are good questions. So now I have 3 sets of coefficients. Now the GPA and HSGPA, those coefficients are linear, so those are sort of interpretable. But the program participation coefficients, keep in mind, these are from a probit model, so you can't interpret those the same way you would the coefficients from a regular linear model. But we're not really concerned about those so much yet anyway. What we're focused on for now is the variance of these error terms and the correlation. So again, on the next slide, I'm going to zoom in on the bottom of this so we can see it a little better. So again, I get the variance of the error terms for the GPA model, primary model, the variance of the error terms for the high school GPA model, but I don't get a variance of the error terms for the program model. Anyone know why not? I've asked this, I've done this, I bet 40 times I've done this talk, only one person's ever gotten it, and you're going to be the second, aren't you?
The coefficient's 1. The error variance is 1.
Now we have 2. Yes. So the error terms for the probit model are constrained to be 1. You know who the other person was? Tinko Rykov at Michigan State.
Ah, okay.
He got it. So I've probably done this talk 40 or 50 times and no one ever gets that, but now we have 2. So anyway, but so the variance of the error terms is constrained, so we don't show it in there. And I'm not sure why we don't just go ahead and show it and say constrained, because we do that in the sim output, but we do get a correlation for the error terms for the program model and the GPA model. We do get that correlation, and it's 0.45. Now in the real world, 0.45 is kind of, it's sort of on the edge. Is that really a strong correlation or not? In real life, I would probably run the model without doing it this way and run a basic model and see how they compare to a sort of sensitivity analysis. But this is a talk about unobserved confounding. So we're just going to say, yeah, it's correlated and keep on rolling with this. So I'm going to say, yeah, that's a fairly correlated, those errors are correlated enough that I'm going to leave this in my model the way it is. So not only have I identified this problem of unobserved confounding, but I've also fixed the problem by using this kind of model. And again, I'm collecting the results, and we'll come back and look at those again in a moment. So any questions up to here? Yes.
Do you have a way of dealing with, like, if instead of a binary variable, you have like a categorical variable? Like how
For the
would,
treatment variable,
yes.
it can be ordinal. Unless something has changed and I just missed it, I don't think there's a way to treat it as categorical, like multinomial. It's going to treat it as ordinal.
If suppose you wanted to like still performance analysis, which you separated into 2 variables, like say it was a variable was like stepwise 0, 1, or 2. So you
Right.
just create 2 and run 2 entry parts in there.
That's an interesting question. I don't know if it will allow you to use the entry option twice. I'm thinking probably not, because what's going to happen is we'll see later on is after we fit this model, there are some post-estimation commands we can use, like estat t effects, and it will show us the treatment effect. And it knows what the treatment variable is because it's whatever you put in this entry option. And that would probably confuse that machinery, that post-estimation machinery, if you had 2 entry options. I'm just thinking out loud. But it might, I don't know. Does anyone know for sure? Has anyone played with this? That's an interesting question. I don't know. It might allow you to do it twice. But what I do know, and this is very unstata-like behavior, this can be binary or ordinal, and there's no option to tell it that. it automatically detects. If you have a 0 and 1, it just treats it as binary. If it's more than 2 numbers, it automatically treats it as ordinal. So you don't have to put comma ordinal or comma whatever, it just knows. And you don't have to type comma probit either, because it only works with probit. So either probit or oprobit, and it automatically switches if it has more than 2 categories. That's an interesting question. I have to go home and try that. Any other questions? Let's ask interesting questions. I do have to stay on schedule. Yes.
So that is a correlation or a covariance of the errors that you're estimating, because you have, some of those variables are treated as continuous. And so it's a variable with an error variance from the probit of 1, and then the error variance for the continuous variable doesn't have to be 1.
I don't know how it's done under the hood, but it is scaled to be a correlation.
Okay.
So yeah, it's a correlation, which makes it easier to interpret because it's bounded between 0 and 1. But I don't know how it's scaled to be that way. That's a good question. Okay, so let's talk about data that are missing, not at random. I'll save the question for later. So data that are missing, not at random, and this phenomenon, this can lead to a phenomenon called selection bias. So let's talk about missingness for a moment. We know we have some missing data. Remember, we're missing some data for college GPA. So let's imagine a perfect world where we didn't have any missing data. What happens here is the freshmen come in, they take all their classes, and eventually they graduate and they get their class rings or whatever. And everyone's happy, including us, because we have complete data and we don't have to deal with multiple imputation or FEML or any of these things. But we know that we don't have that. We have some missing data. So the next question becomes, how did the data become missing? Well, a way that it could become missing is something called missing completely at random, often called MCAR. So here's what could happen. The students go along, they take their classes, most of them graduate, but this guy down here won the lottery. Oddly enough, the weekend after I created this slide, a kid in Florida actually did win the lottery. I don't know if that had something to do, if there's a correlation there, but this kid won the lottery. And he said, you know what? I'm done. I'm going to go buy an island and I don't need any more of this school stuff. So this student never graduates, and since they never graduated, we never observed their final college GPA. Well, that's a bummer for us because we're going to lose some statistical power, right? We don't have the sample size that we had before, but the good news is that it shouldn't bias our results one way or the other, because if it's just a completely random thing like winning the lottery, this kid could have had a high GPA or a low GPA, or we don't know, and it doesn't matter because it's just completely random. If this is what's happening with lots of people, it's completely random. Another way this could have happened is something called missing at random, or MAR. And this is a way this could happen. The students are going along, they graduate, but this person, their mother lost their job and they can't afford the tuition payments to keep going to school. Well, that's a bummer for them for sure. And it's a bummer for us because we're not going to observe their final GPA. But, and again, suspended reality, just roll with this explanation. Let's say the mother lost her job and we have parents' income data in our data set. So we could, and we know there's a relationship between parents' income and final college GPA. So what we could do is leverage the information we have about the relationship between parents' income and college GPA from the known data and use that to use multiple imputation and maybe recover a little bit of the information. So multiple imputation might be an option here. All right, so that's missing at random. This is the one that we really would like to avoid. It's called missing not at random. So here the students are going along, they take their classes, most of them graduate, but this person says, you know what, this is just too hard. I'm on academic probation, my GPA is in the toilet, they're gonna kick me out anyway, I give up, I quit. So this person never graduates. And if we have a lot of these people in our data set, these people are never going to graduate. So we don't observe their final college GPA, but here's our problem. Not only are we losing statistical power, but if a bunch of these people are dropping out because their college GPA is low, that's going to bias our results, right? We're going to have a selection bias problem where we only observe people at the upper end of the GPA distribution. We've chopped off that lower tail because these people dropped out. So not only do we lose statistical power, we may actually bias our estimates of college GPA. So this is a big problem. We really want to avoid ignoring this because we know it could bias our results. And again, we know that we have 208 people like this that are missing GPA data for some reason. So what are we gonna do with this? Well, you guessed it, we're gonna build a model. So we're actually gonna build an auxiliary model for graduate, and we're gonna look for predictors of who's likely to graduate or not. And again, this auxiliary model will have both observed factors and unobserved factors. But this time we're gonna do it a little bit differently. We're going to fit our primary model, but notice that our primary model at the top does not include graduate. Well, let's just skip to the next slide because that makes it even more obvious. When you draw this as a path diagram, what happens here, graduate appears in the model, but it doesn't appear back up here in the primary model. We're not saying that graduation status influences GPA because we never observe it anyway. But what we are saying is that, let's go back and talk about our instrumental variable for a moment. I'm going to fit this auxiliary model and I'm going to use roommate as my instrumental variable. And here's my argument this time. If your roommate is also a college student, you're probably kind of in sync. Your schedules are in sync. You need to be quiet. You need to study. You don't have a lot of chaos because you're both focused on school. But if your roommate is your spouse and your 3 kids and 2 dogs and your mother-in-law who lives in the basement, you got a lot on your plate and a lot of distractions, and that could be influencing your likelihood to graduate or not, just because you have too much on your plate. So roommate, I'm arguing, is related to whether or not you graduate, but roommate shouldn't be associated with your ability. Okay, at least that's the argument we're going to make for our purposes. So roommate works here as an instrumental variable in our auxiliary model. So ability could be lurking in the error term for this model as well. And if it is, then the error term from our primary model and our auxiliary model should be correlated. So again, we can fit the model and check this. But again, I want to emphasize this because this is why we're going to have a third option on our eRegress command. Graduate does not go back in that primary model. All we're doing is fitting these 2 models and allowing for correlated errors. I don't have a good intuition as to why this works, but I'm going to have to appeal to authority on this one. Does anyone know what this technique is called? It has a name. It's named after a very famous econometrician, Tobin. Close. It's called Heckman selection. It's named after a guy named James Heckman, and he won the Nobel Prize for economics in 78 or 79. So I don't have a good drawing or cartoon or anything to explain why this works. I'm just going to have to argue that, well, James Heckman got a Nobel Prize for this, so he probably had some idea of what he was doing. And this is what Heckman selection is. We're going to fit this auxiliary model, but we're not going to put that variable graduate back in the primary model. All we're doing is allowing for correlated errors. So now I have my primary model here at the top, and now I have these 3 auxiliary models. Now notice I have a third option name here. It's called select. Select is going to do something similar to treat. It's going to assume that this is binary, you're either in or out, but it's not going to put graduate back in the primary model. It is going to estimate the correlation between the error terms, but that variable graduate does not go back in the primary model, which kind of argues for maybe I should put these back in that one and then leave that one out to really emphasize that. Maybe I should change that. So if I fit this, now I get 4 sets of coefficients at the top. Again, the graduate and program coefficients are on a probit scale, so we can't really interpret those. And again, what I'm interested in is the error terms here at the bottom. So let's zoom in on these. Again, it's a probit model for that selection model, so I don't get a variance for the error terms, but I do get a correlation between the error terms for the graduate model and the error terms for the primary model. And that correlation is 0.76. So again, that's a fairly high correlation, which suggests that we do have this problem of data that are missing not at random. We have this unobserved confounding issue going on with our error terms. So that's a way to deal with that. It's called Heckman selection, and you can fit it in other models, but you can do that in the context of this kind of analyses here. We don't call it Heckman selection in it. It's just a select option, but that's essentially what it's doing. So any questions up to there?
Is it all maximum likelihood?
Yes. Okay. So yeah, it sounds like it's just some voodoo magic. In fact, some people have called it that, but it's just a gigantic likelihood that you have to maximize, and maximizing it is non-trivial. I think what's actually going on under the hood, it's method of moments. I think that's actually how it's estimated. So I don't think it's true maximum likelihood. I think it's method of moments going on underneath. I could be wrong. But anyway. Okay, so, oh, question.
Oh, but just to point out that in the economics literature, the Heckman selection model is like fallen out of favor. Like it's not really used anymore, partly because economists can never agree. No, on the theoretical restrictions that have to be in the theoretical assumption, which in this case would be like the roommate is an exogenous like instrument. And the fact is whenever they encounter one of these, then they just start arguing about the instruments. When I was in grad school at Michigan, I'm not an economist, but they were not allowed to use Heckman models because they were considered like very unstable. Like if you change these, if you say, well, we don't believe this instrument, let's try a different one, the results are very fragile.
Yeah.
And so like it's true that if the assumption holds, like if you have simulated data, it will work. It's like it is magical. Then in the real world, the fact that like it's a theory, like it can't be proven unless you have a really strong quasi-experimental situation. So, but I do think the real world comes in, which is that it's really hard to find a good instrument.
Yeah, I have zero training as an econometrician. I stumbled onto this recording a video that otherwise I never would have even seen this feature. So I don't know a lot about the real world applications of these. So these are all good points, and the instrumental variables thing I know has a lot of issues, but yes.
If you had an over-identified model, there would be some check on the assumptions that are going into that. You could have an over-identification test, but I don't know if that's an option with the state of procedure.
That I also don't know. That's a good question, and I can check on it and get back to you if you like, but I don't know. This is the problem with talking about the things that are on the far outer edges of my training and experience is I can explain it and make some cartoons, but once you start asking hard questions, I just don't know the answers, but I can check on it for you and get back to you. Yes, another question?
What assumptions are you making about the distribution of the variables that you're putting into the select? And, sorry, not the select, but like for example, the roommate or the income, like what assumptions are you making about the distribution of that data?
We're not making any distributional assumptions. We're just we're assuming that they're either indicator variables or they're continuous variables. So we're either treating them as binary or continuous, but we're not making any distributional assumptions about them.
Except for the probit, you're assuming it's a normal.
Yeah.
Well, the probit part, right? Yeah, but the variable itself, no. We need to wrap up.
usually keep pretty close time on this, so
Okay, so we need
if you have additional questions, I think Chuck could answer them, but please join me in thanking.
Oh. Okay, can I say one last thing? I was going to go through and show you why this works, but this works with survey data. So if you're working with survey weighted data,
That's nice.
yeah, all of this stuff works with survey weighted data as well, which are often observational data. So thanks again for being here. I'm sorry. I'll hang around and answer more questions if you like, but
Thank you so much.
thanks for setting this up.